Hi guys, today I want to introduce standing waves and I want to talk about music and but I'm building on the previous lecture, so make sure you watch the previous one. So last time we talked about driven oscillator. So that means if you have an oscillator like you have a spring and a mass, instead of letting it go on its own, oscillate about its equilibrium position in a simple harmonic motion, then you force the oscillation on it. So you have a driven frequency and you force that frequency on that oscillator. So what's going to happen? So the oscillator is going to shake, of course, at a driven frequency, of course, but the amplitude that you get, the amplitude it will oscillate with, depends on how close is your frequency to the natural frequency. Okay, so it means if here you have a simple spring here with just one mass, so omega sub 0 is going to be k, it's going to be the square root of k over m. Okay, so it's going to be just this. So if you shake that oscillator close to that frequency, you see you get very, very large amplitude if you don't have too much damping. So how narrow is that graph here depends on the damping. So if you have a lot of damping, so you're not going to have a lot of amplitude. So for a small input, you can get a very large output if the frequency force on that oscillator is close to the natural frequency. And there is always this video I like to show. This one, it comes from Mechanical Universe. It's a very old series. You can find it on YouTube. It was very well done. So here, that's a happy oscillator. It has its own natural frequency. Nothing happens to it. Okay, it's doing what oscillator do. Okay, so it's going to describe a cosine here, and the amplitude is whatever it was starting with, and now you're going to force oscillation on it, right? So you have a small force that you apply with a force with a small amplitude, right? And the oscillator start to shake at the same frequency. The waveform may be weird, but it will be the same frequency here. And then what's going to happen if you get closer and closer to the natural frequency, right? So even though the amplitude here is not very large, look, the amplitude that you're going to get here, it's going to get larger and larger and larger. So this is called resonance. It means for a small input, you can get a very, very large output. And boom. So we discussed that last time. So the question is now, let's say instead of having only one mass, you have two masses, or maybe you have three masses. Okay. So you can have, for example, a building. A building, you can have a model of a building with a different floor, and each floor has different masses, right? And that building can shake in different ways. So here we have two masses. What's going to happen? So in that case, you're going to have two natural frequencies. So it means you're going to have two resonance frequency. You're going to have a low resonance frequency and a larger resonance frequency. Okay, so you're going to have two masses. And this is called a coupled, it's called coupled oscillators, because you see those two masses, they are linked together by spring. So everything is linked here. So what's going to happen to it when it oscillates? So let's look at a demo, very good demo here. So let's go back to the first case, which is an easy case here. You just have one mass, two springs, for example. And if you shake just once, and then you let go. So you let go here. So you have the amplitude here, A. You see it's going to start to shake at its own frequency. The frequency is square root of 2 times omega 0. So we did that problem together. If omega sub 0 is square root of k over m, just from one spring, if you have a mass with two springs, and let's say those springs are the same length, the same stiffness, then the natural frequency is square root of 2 times this. So by the way, I have found the website here. It's part of Wolfram Alpha, and you have the math here. So you can look it up. And that's what we found, right? But if K1 equals K2, so then you're going to have 2K. So 2K means square root of 2 times omega 0. Okay? So if you have one spring, just one spring, just one spring here, there is no just one spring, so, okay, smallest one is, okay, nothing special here. It starts with two spring and a mass. Okay, so let's go back to my simulation. I lost it here. Now, this is called the longitudinal oscillator. So you have only one natural frequency. That means you have only one mode. Okay, it's called the normal mode. Now you can disturb it in this direction. This is called the transverse oscillator. So it's going to go up and down. You can change the amplitude if you want, but it's doing its own thing, and it's going at its own natural frequency. So let's see now if you have two, not three, just two. So if you have two, can you think of two ways these two can oscillate? Can you find its two normal modes? So if you think about it, you can stop the video, or you can see that the two masses, they can either shake, in phase, okay, with the same frequency, the same natural frequency. So that will be the lowest one, okay? They can do this. Or what they can do this. Squeeze together, move away from each other, squeeze together, move away to each other. So that means you have two modes and two natural frequencies. So when they move together, you see that this is 0 and this one is 0. So this one moved to 1, this one moved to 1. This one moved to -1, this one moved to -1. So these are called eigenvectors, right? The way they move relative to the equilibrium. So if they squeeze, so they are pushed together and then they are pulled apart. So push, pull, push, pull, push, pull. That's the second mode. And they are out of phase. That means if this one was 0, now it's -1, but this one will be 1. So -1, 1. Okay? So I'm not going into the math at all. I just want you to understand the concept. So here, let me show you. I'm going to put the first mode. How do I put the first mode? That will be, no, I want them to oscillate like this. Okay, so that will be the first mode. And you see, they are in phase. And the natural frequency is just omega 0. Okay, in that case. The second mode will be when they are pushed together, pull apart, right? So that will be the second mode, and it's also, it has also natural frequency, which is, I think it's square root of 3 times omega 0. So you always have a lower one and a larger one. Okay, so these are natural frequencies for oscillators. So anything that wants to shake have their own natural frequencies and natural mode. Now, usually you don't let them shake the way they want, right? So you excite them, you don't know how they respond. The way they're going to respond is a little bit of both, right? So it means it will be a little bit of the first mode, a little bit of the second mode, right? And it looks chaotic, but it's not. Because actually, if you do the math, it will be the superposition of the first mode and the second mode. Okay, so I will go back to this, but first I want to show you. So there is a video. So if you want to do the math, there is a video here. Okay, so this he he has 3 lectures where he goes through the math, right? So to do the math, you have to find the 2 equation of motions, and then you have to use what it's called algebra, linear algebra, okay, to find the frequencies. So if you skip just at the end of the video.
Hey, Miami. Google Fiber Web Pass is expanding in your area. We're bringing award-winning.
Go back to the.
So if you go to the last part of the video, you see that you have your 2 resonant frequency, the 2 natural frequency here.
In the next video.
Actually, I have it. So anyway, so that's just for those who wants to be engineers and they want to learn how to do it. It's not that hard. It's just a linear algebra. So if I think I have like somewhere here. So I recommend the video if you want to look at the math. But you see here the 2 natural frequency, you have omega 0. And here, if the springs are the same, you're going to have 1 plus 2 is 3. So square root of 3 times square root of 3 times omega 0. These are called eigenvectors or normal mode. It just tells you that if one is moved by 1, the other one also moved by 1. So they will be always in phase. This vector here is called the eigenvector. It just tells you that they will be out of phase, the second one. So when one moves this way, the other one moves in this direction. So they will be always out of phase, right? So it's a very interesting math. And if you know the methodology, you know it's not that hard. You just have to solve system of 2 equations with 2 unknown. You can find the eigenvectors and the eigenvalues. But usually you don't have to worry too much because we have computers to do that work for us. Okay, so let me see what else. I have another one with actually let's look at the simulation again. So now you can have 3. So 3, you can have 3 natural frequencies. So you can have 3 modes, right? So the modes are just the way are they in phase with each other, how they will position themselves relative to their equilibrium position, right? So you have the 3 frequencies here. So let's put the first one. Okay, that you could have guessed. Okay, I'm going only up and down here. So that will be the first mode, right? So they are all in phase and they all move at the same frequency. So that will be the lowest frequency. And then I have frequency number 2, the natural frequency number 2, which is the square root of 2 times omega 0. And this one doesn't move. So this one has a eigenvectors 0, 0. And this one, when it's 1 is 1, the other one is minus 1. Okay, so they will be out of phase. And then number 3 will be this one. And this one will, so they all shake at the same frequency. That will be the natural frequency. But you see, then you have to decide, are they in phase or out of phase? Now you can make longitudinal oscillations. So this one, we have this one. Okay, that makes sense. Okay, they are all in phase and they all move at the same frequency. Or they could be that way. Okay, that's a cute one. So this one doesn't move. Similar to the previous, to the transverse oscillation. Or you can have this one. It's more complicated. But in real life, when you're going to start to excite it, right? Or you're going to move it, right? So maybe this is a building with a three stories building, right? So 3 floors. And here there was an earthquake, or there was the wind, start to shake the building. The building will only pick the natural frequency, and you will have a cocktail. It will shake with a cocktail of the 3 frequencies here, or the 3 natural frequencies. So it looks like very chaotic, but actually it's not, because if you do the math, that's going to be the superposition. You can describe it as being the superposition of the three modes, right? So you will be able to write that what you get, x1 for the first mass, will be a superposition of the 3 modes, right? With the 3 natural frequencies. So that's the secret. So now we'll go back to that in a moment. Let me show you. You can have also you can have a couple pendulum as well. So for example, this one. So if you look at these pendulums, you have 2 pendulums, huge one, and they are connected by a string. So that means they are coupled oscillator. So it's very hard to predict what the oscillator is going to do, right? It looks chaotic, but actually it's just a superposition of 2 modes. You see how it's behaved? So this one picking up the oscillation. This one is going to stop, and this one is going to move instead, right? So this is called a coupled oscillator. It's called a coupled pendulum, and you have also 2 modes, right? So either the 2 will move at the same frequency together, or they could be out of phase with each other, and you excite them randomly. It will be a combination. It will be a superposition of the 2 modes, right? So that's what you see here. Now, so I do recommend a lot the lectures by Walter Lewin. I don't know if I have it here. So I'm going to show you a video that comes from that lecture here. He has amazing physics lectures. You have 801, 802, and 803. So let me show you. So here you have 3 masses, okay? So it's coupled oscillators. So you have 3 masses here, and they are all connected with a spring. And before that, he did the computation of the normal mode. So it means each one, its position relative to its equilibrium position when it has its natural frequency. So he's going to show you the natural frequency of this system.
And they're not going to move because I don't have any air. Then I turn on the air, and they are immediately free to go. In other words, if I offset this one in the positive direction.
So it's going to look
over a
for
distance
the
1.
natural mode,
We've just
right?
called this positive. I apologize for that.
So this one
because
has to be at 1.
Call this positive.
This one has
and the other
to
one
be
has to be offset by 1 in the same direction,
1.
which I just did. But this one has to be offset by the square root of 2, which I just did. And now turn on the air, and I just have exactly the right initial conditions for this mode. So it is going to oscillate in the superposition of 3 normal modes, but there is only one, and that's the one you're going to see, because I chose the initial conditions. You ready for this?
So that will be the first mode. We have seen that,
Now,
right? So they are all in phase, and they are moving at the same frequency.
They are all in phase.
That will be the lowest natural frequency.
That was a criterion for normal mode.
The lowest resonance
They're
frequency.
in phase. They come to a halt at the same moment in time. They all have the same frequency. And the amplitude here is square root of 2 times larger. That is not so obvious. But you see, this is a criterion for normal modes. Same frequency and in phase. This one. Okay, we're going to put this one at 0. I'm going to put this one at +1.
So that's the one we saw when the middle one is not moving, and only
1.
those two
now,
at the edge are moving.
This one is offset by 1
So this
in
one
this
should
direction.
not move, and
this one is offset by
2
1 in this
others
direction,
should move
and
this
this one
way.
is not offset. I turn on the air, what do you think will happen? That's right. It's going to oscillate in the superposition of 3 normal modes, but there is only one. That's the omega plus. Impressive, isn't it? Next one. This one. So we're first going to put this at 0, this at 0,
So if
and we're going to put this
how
at
the
0,
system
and now
will
what we have
react,
to do, this
the way the system will react depends on the initial condition. So of course, if the initial condition is exactly the natural mode, so of course it's going to oscillate at its natural frequency. If you move them like randomly, so this one will be here, someone will be there, this one will be here. So then what you get will be a superposition, a weighted sum of all the modes, right? So it will be a superposition of the normal modes. So that's the way it works.
has to be put over +1. +1. The other one has to be put minus the square root of 2, and we have measured that here. And it comes so close that this spring is not going to like that. And now this one is going to be, again, +1 in the same direction as this one. That's the highest frequency. And there we go. You ready? Three, 2, 1, 0. One and only one frequency. And every adjacent one is out of phase with the other. These are out of phase, but these are in phase, because these are out of phase.
Okay, so I think it's amazing demo, very good demo. And so let's go back to the simulation here. Again, we had 1, 2, 3 of them. So let's see if we find the same. So the first mode, no, I want this one. So the first mode, you see they are all in phases with each other, right? So they're going to move by 1 relative to their initial position. So the eigenvector will be 1, 1, 1. And then this one will be the second mode. That's the one where this one is not moving, only those two are moving. Okay, so they go to, they are out of phase with each other, right? So one is 1, the other one is -1, and this one is 0. Okay, so I can have -1, 0, and 1. So this is called the node because it's not moving. And then you can have the third natural frequency here, right? and they are always, these two are always out of phase, and these two are always out of phase. Okay? And if you disturb them randomly, then what you get is a superposition of the three normal modes. But it's a superposition. Okay? It's going to be linear. So what you get here, the math will be described. So x1 is the displacement of the first one, for example, is a superposition of the three normal modes. So here there is another YouTube video that I recommend. Here it's called Understanding Vibration and Resonance. The channel is called The Efficient Engineer. And you see this, you have three masses, so it's coupled. The oscillators are coupled, and it's in civil engineering they use that to understand how a building. So if you have a building with 3 floors, will react to wind, for example, or just to an airplane passing by. So here you have the math. You don't worry about that. The solution of this system will give you the 3 natural frequencies and the 3 normal modes.
Or an undamped single degree of freedom system. A single degree of freedom system has one natural frequency and can only vibrate in one way. But since our model has 3 degrees of freedom, it will also have 3 natural frequencies. And at each natural frequency, the system will vibrate in a specific way, which is called a mode shape. Exactly how the system vibrates in practice will depend on the initial conditions that are applied.
So you see, it depends on the initial condition.
For the 3-story building, the 3 modes of vibration will look like this.
So, okay, that was the point of this video here. Very interesting video, because you see how we apply physics here, right? So you see a building will have 3 modes of vibration, and any shaking, when it's being shaken, maybe by an airplane passing by or a hurricane, for example, it will shake in a way that it's a superposition of the 3 of them. But if you shake it at a frequency close to either of those modes, right, either of those natural frequency, then it could be a disaster if it's not seismic proof.
As the number of degrees of freedom increases,
so you recognize the first one, they are all in phase with each other. Then the second one, you have the one at the center that is not moving, and those 2 are out of phase. And the third one, this one is out of phase, and this one that will be out of phase of that one.
To determine the natural frequencies and associated mode shapes.
So that's
We've only covered mass spring models.
Okay, so I do recommend this video here. You have the link in my slides. What else do I want to show you? You can, so here, 3 masses again. So you're going to have 3 resonance frequency, right? So if something shake those systems here at this frequency or that frequency and that frequency, then you can have resonance, right? It can be very destructive. So you can, there was in the same video, here, from the same video by this video here, there is a great demonstration at the end.
Resonances.
And you can also find the modes, the normal modes, if you have a pendulum, right? So, for example, if you have 2 pendulum connected to each other, then you're going to have 2 natural modes, okay? They can swing together like this. So that's going to be just a pendulum. So the frequency will be the square root of G over L, or they could be out of phase with each other. So to find the frequency, I refer you to that video. Okay, so it's a lot of math. Or instead, you can have a pendulum made of 3 masses. So then again, you're going to have 3, 1, 2, 3. And you have 1 and 2 and 3 modes, normal modes.
And then I want you to eyeball these ratios C1 over C2 and C1 over C3. Oh, no problem. No problem. There we go. All right, so now this is the knot where the length is the same. So to get this one into the lowest mode is easy for me. I'll just give it a swing and then let it go, and then we'll just do nothing. And then
So that will be the
I will stop
first
even driving
one,
it.
the first natural frequency, the lowest one.
Now it's nicely in that mode. You see the bottom one has a... Notice that the lines are never in the same direction. You see the offset of the angles? Can you all see that? So our first picture on the blackboard is quite accurate. Now the second one, that's harder for me to find. I mean, we'll first make sure that they're not moving. Okay, so I'm going to try to search for it. I got it. That's it. So the first solution is the correct one. The upper two are in phase, and the bottom one, look at the large amplitude of the bottom one. That's not so intuitive. The bottom one is out of phase with the upper two. Can you see it? Normal mode. Why is it a normal mode? Because they all have the same frequency, and they're in phase or they're out of phase. Now the highest frequency. Now the highest frequency, let me see whether I can get that one. Got it. That's it. Now look how small the amplitude of the bottom one is. And that can all be calculated. I'll do it once more. They're beginning to rotate a little bit. There we go. That's the third mode. So now you know everything there is to be known about coupled oscillators, but the most important thing that you are resonances. And then I want you to eyeball these.
Okay, so I think, oh yes, I have another one. So this one, this simulation was made with MATLAB, if I remember, and it was made by this professor here. I think it was in the last video. He shows that. So interesting also. So
if you look at this first...
So this one are 2 coupled oscillator, and they have been disturbed in a random way. So it seems that they respond also in a random way. But actually, what you're going to see here is a superposition of the 2 normal modes, right?
The clip of the video, you'll see this random motion that we saw initially. The motion doesn't look simple, but in fact it is simple. Now let's look at the normal modes. So the first normal mode has a frequency of the square root of little k over m. It's when the masses are both moving together to the right and to the left. The second normal mode has a frequency of little k plus 2 big K over m, square root, and it's when the 2 masses are moving opposite each other. The left mass is moving in to the right, and the right mass is moving to the left, and vice versa. So we see that the first random motion is simply a superposition of these 2 simple.
So each time you have a couple oscillators, and when you play music, that's going to be the case. You have couple oscillators. They look like they are moving randomly, but actually it's a linear superposition between the natural modes, right? And what you get here, how much of this you're going to get and how much of that you're going to get depend on the initial condition.
Motions. Okay, let me. So if you look at.
Okay. So you get that math. You can watch this video to see how to solve this problem, but it's not in the scope of my lecture. I just want you to understand the principles. And what else? Okay, now let's go back to the simulation here. And then you can have many and many and many more coupled oscillators. So if you have 6 of them, then you're going to have 6 natural frequencies, right? You will ask the computer to do the computation for you. So if you have a longitudinal oscillation, so that's one of the modes here. And that will be the lowest mode, easier to compute. Then will be the highest, larger mode here. And then if you disturb, so that you will get only if you disturb them the right way, like he did in the video. But if you disturb the oscillators in a random way, so then you will get a cocktail, right? You get a little bit of this one, a little bit of that one. So it's like a weighted sum of all the normal modes, right? So it's very important in physics, it's very important in chemistry, it's very important in civil engineering, in seismology. So I can go in 2-dimension somewhere. Yeah, I can go in 2-dimension here. You see, I have also modes. Let's see. I don't know how to make it slow. Oh, I have to disturb it, of course. So if I disturb it, you see, they don't show you the normal modes, but you see you have little bit of this one, little bit, none of those. Okay, so you have a superposition of all the normal modes, even though you don't see the normal modes here, but you see the superposition. You can go this way. I don't know if I can make many of them, like inside molecule, for example, inside this could be molecules connected to each other or atoms connected to each other, and you disturb and it's gonna respond. So I think that this is very cool. Okay. I think we cover everything here. So finally, so what's the conclusion here? Conclusion is that if you have connected oscillators, right, then you disturb these oscillators, it will oscillate in such a way that what you get here is the superposition or the weighted sum of the normal modes, right? So inside that red wave form, you have two sine wave or two cosine wave here, the purple one and the green one, and you add them together. Okay? So it's like you take two normal modes, you add them together with a weighted sum, a little bit of this one, a little bit of that one. At the end, that will be the oscillation that you get. And this is the math behind Fourier. So Fourier says that any complex wave, you can express it as a superposition, linear superposition of cosine wave and sine waves. Okay, so let's connect to standing waves and to music. So now imagine you have a string here, it's a violin, and you can imagine that violin here, that the string is made of many small oscillators that are coupled, right? That are connected with each other. So that could be atoms, right? That make up the string here, and all the atoms are connected to each other. And you can disturb this string here by plucking it, just or by using a bow, right? You can shake it up and down a little bit, so you can move it in this direction. If you have a flute, you can move it in this direction. So you can create a transverse wave, or disturbance, or longitudinal disturbance, right? So with this here, since you have an infinite number of oscillators, you're going to also have an infinite numbers of natural modes, infinite numbers of natural frequencies, right? And we can look for those natural frequencies. So for example, I have a great demo here. I think it's here. So you have a string here. It's a part of a violin. And if you disturb it just the right way, so you pluck here just in the middle, then you get the first natural frequency. So this is called the fundamental, and this is called the first harmonics in music. But it's the same idea. You see, you remember what we we were looking at here in one dimension, when you have many of them, you see, this one is the first, will be like the first harmonic that you have. So you get the same thing with the string here. Okay? So then the second harmonic, it's when the one at the center here, you have a node and it's not moving. So that will be the second mode. Okay? Will be a frequency twice the first one. And that will be like the one here. So you see how at the center it's not moving. I have a node here, and this one is moving and that one is moving. Then you can have the third harmonic, right? So we have 1, 2 nodes. I mean, actually, this is also a node. It's not moving. So 1, 2, 3, 4 nodes. Those points are not moving. That will be the third harmonic, or the third normal mode, right? So the third one. And again, if I go back to my simulation here, I have the third one. Looks a bit the same, right? So as you increase the number of oscillators, you see I'm very close to a string here. Because the string is like connected oscillators. And then you have the fourth one. So 1, 2, 3, 4, 4 bumps. And you have the fifth one. So as you increase the harmonics number, of course, you're going to increase the frequency. Now, in the real life, when you take your violin and you use a bow, okay, so you're going to expose the string to a whole bunch of frequencies, okay? So if you are exposing it to frequencies that are not its own natural frequency, it will ignore it. But as you play the violin, it's going to take all its natural frequencies and mix them together in a superposition, like in a cocktail. And that cocktail will make a violin, right? It will determine the quality of the tone or the timbre. So when you are playing a violin, what you get is a mix of all the harmonics. You're going to get the first one, the second, the third, the fourth, and the fifth. And how much of each do you get? So maybe you're going to get a lot of first, little bit less of second, none of the three, a little bit more of the fourth, and so forth, that will make the violin sounds like a violin. So it's like a recipe, right? But now your ear will only perceive the pitch of the first one. It will not be able to detect all the other harmonics. It will only detect the first harmonic. So that will be the pitch of your instrument of music. So you can see here that the sound that you hear, the wave form here, they can visualize with an oscilloscope. It's made of a superposition of all the other harmonics. Okay, so that's how music works. So let me show you. Just skip a little bit further here. If you play so if you play the same note, so that's middle A, you can detect if it's a tuning fork playing a flute, a violin, or a singer, because even though it's the same note, when you see how much of each harmonic will be different for each instrument. So if you play a tuning fork, that's going to be very, very boring, because it will only keep the first harmonic, okay, the fundamental, the first natural frequency. If you have a flute, it's a little bit less boring, and you're going to have a lot of the first, the second, the third, the fourth, and then not many of the other harmonics, right? If you have a violin, that's more interesting. You know, it's very rich here. You have a little bit of all the harmonics here. Now your ear will only detect the fundamental, which is the middle A, right? Even though everything else it's mixed together. So if you are a singer, of course, we cannot, we don't have the possibility to include all these other harmonics. So each instrument here will make its own cocktail when you're going to excite it, right? So if you use a bow, for example, for the violin will choose, okay, I'm going to take this one, a lot of the first, a little bit less of the second, more of the third. And when they mix together, that will be the timbre. That means the tone quality. And that will help you make the tell apart a violin from the flute. So, for example, here I have a piano somewhere. Where is my piano? I lost. Here it is. No, it's not a piano, it's a guitar. You see, when you play the guitar, I don't know which note you are playing here, but you see you have some of the first harmonic, second harmonic will be more, which is twice this one, third harmonic, fourth harmonic, and so forth and so on. But it's a very special cocktail. So what you hear is a superposition of all those natural modes. And the pitch will be the frequency of only the fundamental. With your ear, you are not going to hear the other ones. Okay? So I hope it's clear. So any wave form here, right, when you are playing music, is actually the weighted superposition of all natural frequencies. And the way it's mixed depends on the instrument. So let's go back to my string. I was talking about the guitar here. So I did a demo for a class here. I think it's this one. Okay, so you have a string here, and I have a driver, and I was looking for the harmonics, right? So I excite it at 10 Hertz, and I get the first harmonic. Of course, it will depend on the length of the string and the tension in the string. Now I'm gonna increase, then everything die until I'm driving it at the second harmonics. second harmonics will mean the second natural frequency, 20 Hertz. And then I get to the third harmonic, so 30 Hertz. So now you see 1, 2, 3. So that's the third natural frequencies or the third normal modes. And then nothing in between 30 and 40. And then 40 you have 1, 2, 3, 4. Right? So that's, by the way, that's what we call a standing waves. Standing waves because it seems it doesn't move. It seems to be standing, not moving. You don't see the wave moving back and forth. Okay, so actually what's happening, you do have a wave moving back and forth, but the forward wave will interfere with the one that is reflected, and they interfere with each other, and that's why you get standing waves. So I am at 50, so I'm going to get to 60 Hertz. So you have 1, 2, 3, 4, 5, 6. This is my driver here, so it's shaking at the right frequency. I don't know how high I was able to go. 7. So 1, 2, 3, 4, 5, 6, 7. So you can do that also with a slinky. It's a very famous demo. I don't know if I have it here or here. So that comes from a website.
Okay,
for a website, if it's a YouTube channel, it's called Physics Demo. So you can do the same thing with a slinky.
It's called mode, M-O-D-E 1.
So that will be the first
or
one.
the first harmonic, or in other words, also called the fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode,
You get the 2.
I get
1, 2.
the second harmonic, or second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where there's approximately no motion going on. 2, 1, 2. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic or second overtone.
It's hard to get, right? Almost.
Let me try again.
But you get the point. So now another here, very cool. Look at that. You can visualize the wave. The normal modes, the natural frequency. So very cool. Okay, I think that's all I have for you for simulation. So let's go back to music. So again, I recommend that you play with this app. You see the third harmonic here. You have 2 notes here. You can have less. So always that's going to be the first harmonic here. The second harmonic, you still have your note here. The third harmonic here. So this one is not moving. This one is not moving. So you get you see how it works, right? And then, of course, if you disturb it randomly, so it's going to start to shake in an interesting way, which is a superposition of all the modes. right? So if you take all this waveform, you add them together in a weighted sum, that's what you're gonna get at a time t. So let's go back to music. So we did the violin. Flute. So a flute is made of I don't know what. Okay, flute. Flute is also okay. So now let's start. Let's look at the flute. So a flute is a wind instrument, and it's open at both sides. So that means here and there. So here and there, the air can move, right? So you make the music here because of a sound wave. So it's like the air is made of many oscillators, and those oscillators will move in a longitudinal oscillations, right? So they can move only in this direction. With a string, you get transverse oscillations. So if you go back to my simulation here, you see that that's going to be longitudinal. That's going to be longitudinal, right? So let's go back to the flute here. I have the first harmonic. So the node is here. These are called antinodes. So because here it's open, here it's open. That's mean the air here at that point and this point will vibrate, right? So it means the air will be squeezed and then stretch out and squeeze and stretch out. They are not forced here not to move like a string. If you remember the string here, at both ends, I had antinodes. So it means this part and this part, they cannot move. With a flute, this point here and that point here, the air is free to move. So that will be the first harmonic. So you don't want to look at the white here, you want to look at the green. So the green is the second harmonic. I can make just the green here, second harmonic. And then you have the third in blue. In blue, that's the third harmonic. And in white is when you combine them together. That will be the fourth. So I can have the fourth alone. So you can visualize that will be your fourth one. That will be the fifth one. That will be the fifth harmonic. And then you can combine them together and you get the white wave. Isn't that a fantastic simulation? So you can use that website here. Then we can, the last thing that we can have, so it's like a piano, kind of a piano. It's a mini piano, but you see here, this part here of the stick here, cannot move. So here I need to have a node, and at the end it can move freely, so I have an anti-node. So here it doesn't move, at the end it's moving. So that will be the first harmonic. And we're going to compute those harmonics, okay, in the coming lectures. But this is the idea behind a clarinet, for example. If you have a clarinet, this here, it's the mouth piece is closed, and this part here is open, so it can move freely. That will be the second harmonic in green, and then it's going to be one. Actually, I don't have second harmonic. I can have only the first, the third, the fifth, the seventh, and the ninth. They are only odd numbers. We're going to see that next. But you see all the harmonics here, and when you combine them together, superposition of all of them, you get the white wave form. Okay? So I think that's it for today. You see, when you are playing music, It's just a superposition of natural modes, except it's a linear superposition and it's a weighted sum. So maybe you're going to put a little bit of this, more of that, and more of this, right? I think that's all for today. So next we will look more at standing waves. Okay, and I have put here in my slides the videos I have used. So this is a very nice lecture for engineers. So if you want to do the math, if you want to learn how to solve those coupled oscillators, I recommend this video here. This video is also very nice to watch from the beginning. And then this is a classic.